Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to continue looking at how we can measure liquid mixtures. But it turns out one of the best ways to do it is actually to measure the gas. So we can really show this by the idea of if I have a mixture of two components, A and B, I want to try and figure out the chemical potential of each of these components in the liquid phase. If I don't know this, I can figure out a lot about things like the Gibbs free energy of mixing and all kinds of other properties. Now, what we can do is if both of these components are volatile, this means they'll both be producing a certain amount of gas. And it turns out, as we've seen, gases are a lot easier to model. So we can use the fact that if I have a relatively small enclosed container, the gas and the liquid should both be at equilibrium. So that means the chemical potential of my liquid mixture will be the same as the chemical potential of my gas. Well, and I know how to model the chemical potential of the gas a lot better, as we saw last time. It can be simply given by the standard state chemical potential plus RT and then the natural log of whatever the pressure is. So if I know the pressure of the gas, and I can look up the standard state chemical potential, I can figure out the chemical potential of the liquid. Works great. We can then use the relationship, so for a pure liquid, that we're going to designate that the pure liquid is given by a star. So the chemical potential of the pure liquid should just be equal to the standard state chemical potential plus a correction term in terms of the vapor pressure of the pure liquid. And again, as we've seen, you can often go ahead and look up the vapor pressure for the pure liquid and determine it from a simple phase diagram. So this works relatively nice in that all of these properties are ones I can readily determine. Now, what we can then do is try and express both of our equations in terms of the chemical potential of the gas. So we can try and look at instead what's the standard state chemical potential of the gas. So isolate this. So the gas is going to be equal to the chemical potential of my liquid mixture minus RT of the natural log of the pressure of the mixture. And it's also going to be equal to the chemical potential of the pure liquid minus RT of the vapor pressure of the pure liquid. So we can now use this to relate information about the mixture to information of the pure substance through a nice equivalency. What we can now do is rearrange this to figure out the chemical potential of the liquid mixture using our standard state, using the pressure of the gas above it. So by moving the RT term over to the right, so we add it to both sides, we now have the chemical potential of the liquid mixture is equal to the standard state, or to the chemical potential of the pure liquid minus RT, and then we have these two pressures. Well, notice they have the same prefactors, so we can just combine the natural logs. So we have now RT natural log of the ratio of the vapor pressure of the mixture over the pure vapor pressure. So again, chemical potential of the pure liquid, we know we can look that up in a table. Vapor pressure, we can determine this from our phase diagrams. So the only thing we need to know is if I know the vapor pressure of A in my mixture, I know the chemical potential in the of the liquid in the mixture. So this is actually really nice. And what it shows is that we can figure out we can define the stability of A based on the partial pressure of the mixture. Now, there's a slight problem. It's kind of hard to determine the partial pressure of a single component in a gas. So we'd much prefer if instead of using the partial pressure of A, I could define it in terms of a liquid property. So instead of defining in terms of the gas, if I could define in terms of the liquid, that would be amazing. Now, as long as the intermolecular forces in the liquid phase, in between A and B are similar, they should be identical in A, or in the gas, they should be nothing. But as long as the intermolecular forces in the liquid are similar, what we find is the vapor pressure of A should go ahead and match with the concentration. So what we can then do is if I have similar intermolecular forces in between A and B as in between A and A, then the partial pressure should be given simply by what would be the vapor pressure of a pure mixture times what fraction of that mixture is A. And this actually means it'll map onto reality fairly well. Because if I have a pure liquid, the mole fraction is 1, and the vapor pressure is the pure vapor pressure. Works great. If there's no A, then the vapor pressure is 0, which makes sense. There's nothing to evaporate. And it should be a nice linear correlation. And this actually holds fairly well as long as these intermolecular forces are fairly similar. When we do this, we end up being able to literally take our equation in terms of the chemical potential of the liquid mixture as the pure liquid plus this correction term in terms of the concentration of A. Now, the problem here is that this does assume that the intermolecular forces that A experiences the same as the intermolecular forces it experiences with B. But if this does hold the case, then we have a nice linear variation of the partial pressure of A along with its composition, and the same thing with B. Now, mixtures that follow this rule are called this Raoult's law are called ideal solutions, and there are plenty of them. This will be things like benzene and toluene. They differ by a single carbon. The intermolecular forces are relatively similar, so we expect fairly similar values. You'd also expect this to hold for things like N-heptane and N-octane. That extra carbon doesn't make much of a difference, so we get nice, simple behavior. And in this case, not only can the partial pressures be given as a line based on this description, we also find that the total pressure can be given by a straight line in between the two components. So this gives us nice, relatively simple behavior. The problem is what happens if the intermolecular forces in between the two systems are different? Well, it turns out in this case, then we get deviation from Raoult's law. And it turns out the Raoult's law will tend to break down the more that I have of the solute I have present. So for example, let's take a look at this idea in terms of a mixture of carbon disulfide and acetone. If I have a mixture of pure acetone, I'll have the vapor pressure of pure acetone. Adding a little bit of carbon disulfide doesn't change the intermolecular forces of acetone that much. But the more of that carbon disulfide I add, the more I disrupt the intermolecular forces and the more I tend to deviate from Raoult's law. By the time I'm mostly carbon disulfide, the vapor pressure of acetone is very dissimilar to what I'd expect from Raoult's law, until by definition it has to go to 0. Similarly, but to a lesser extent, we see the same thing with carbon disulfide. We tend to see when I have a solution of pure carbon disulfide, I get the pure vapor pressure. And in this case, instead of holding up until about a 90% mixture, it only holds to about 97, 98 before we see that deviation. So the carbon disulfide has a much more pronounced deviation than acetone. But generally what we're seeing is the Raoult's law tends to hold best when that mole fraction is close to 1 for either of the components. Note that we have a very significant deviation for the total throughout, so we're really just looking at the components. And as a result, we tend to say that Raoult's law is a very good description for a solvent system. It holds very poorly for a solute, but if I've got a solvent and it's a relatively pure solvent, I can use Raoult's law fairly well. But what we need is a much better way to describe solute behavior. So next time, we're going to go ahead and look how to describe solute behavior as we really dive in to non-ideal mixtures. Until then, take care.